Hello everyone. In this video we will discuss about strong and weak acid and bases. So the definition is kind of pretty simple. Strong means obviously something strong and weak means obviously something is weak. So let's start with strong. So anything a strong acids or bases. So strong means an acid or basis that dissociates in water almost entirely. So, what do I mean by dissociates? So, here's an example. Let's say we have an acid HI, so which is hydroiodic acids. So, HI, and you put them in water, and what's going to happen? It's going to dissociate entirely. So, H1, so HI would be splitted into H plus ion and I minus ions. So this is an example of strong acid. So similarly, if you have sodium hydroxide and you put them in water, and you're gonna get sodium plus and OH minus ions. So these are the strong acids and strong bases. So HI is a strong acid and sodium hydroxide is a strong base. So when you put them in water, they dissociate entirely. So like think it this way: if I put 100 molecules of sodium hydroxide right here, immediately what's gonna happen? You're gonna get 100 sodium plus and 100 OH minus. So if I have to draw a graph, so if I put 100 of here, so if I put 100 sodium hydroxides here, immediately what you're gonna notice is you're gonna get 100 sodium plus and 100 OH minus ions. So that's an example of strong acid and strong bases. So this is base. Similar things will happen if I put 100 HI, I should get immediately H plus ions and I minus ions. So usually H plus ion does not stay by itself. So usually how do we write the acid equations? We can write something like this: Hi plus water. So you're gonna get H3O plus and I minus ion. So usually H plus ion doesn't stay by itself. It's react with the water because you are putting into water. So it becomes H3O plus and then stay as it is. Okay, so that's a definition of strong. So what should be definition of weak then? So weak acid, it's pretty easy. You can write by yourself. So weak acid or a weak base that does not dissociate entirely. So that's does not dissociate entirely. So HF is a weak acid. So HF is a weak acid. So if we put them in water, technically what should you get? H plus and F minus, right? So here is what happened. If you put HF into water, let's say you put 100 of them here. If this would have been a strong acid, you should have got 100 here, 100 here. And then it's going to be 0. Because if you put 100 of them, they immediately switch to 100 of these, 100 of that, right? So you should get something like this. But because this is a weak acid, so if you put 100 here, let's say you started 100, 0, 0. After a few, if you give some time, you're gonna get probably 99, 1, 1. So that's the ratio I was talking about. It's gonna be extremely small. So it's this very small amount of HF would be dissociated into free H plus and F minus ions. So in this portions, this is a definition, this is an example of weak acid. So what happened is whatever H plus and F minus you make, they're gonna be immediately switched back to the reactant side, which is HF, to recreate this one. So that's why you always gonna get more of this and less of the dissociated portions. So more, less, and less. So usually the weak acids and bases are weak electrolytes. So these are called electrolytes because they are dissociating. But because weak acids and bases, they does not dissociate entirely. So that's why they call weak electrolyte. And the strong ones are called strong electrolytes. So you can see in strong acid and bases, we point the arrow to one directions, but in a weak acid or basis, we point the arrow on either directions. So because the reaction is going on either side. So again, quick recap, a strong acids dissociates entirely. So maybe I should redraw here. So if I dump 100 sodium hydroxide here initially, I should get 0, but after instantly, like after a few microsecond, millisecond, nanosecond, whatever you want to call, all the sodium hydroxide is going to change. So you should get 100 sodium plus and 100 OH minus. So almost everything is going to change to sodium plus and OH minus. So that's why you see the arrow is one directions, and you might see arrow on both directions. So let's do another example. So it's called acetic acids that is present in your vinegar, CH3 COOH. So this is acetic acid. We will see this compound later. This is present in your vinegar. So this is a very weak acid. So what happened? This proton here, so when you put them in water, so this proton gonna react with water, and it's equal, not equal, like the arrows on other directions. So you would get CS3COO minus because proton is gone. And what would you get? H3O plus. Can you identify a conjugate acid base pair here? Let's do it. So on the left side, this is act as an acid because this is the one that's providing proton. What is its counterpart on the right side? This is the counterpart. So this portion is called conjugate base of that acid. On the right side, sorry, on the left side, water is the one that is accepting the proton. So this is accepting the proton. So this means this is our base. What is its counterpart on the other side? So this would be our conjugate acid, Ca. All right, so let's stop this video here.